Okay, in the last video, we were attempting to evaluate this integral here, and we made the substitution. We said let this be equal to a new variable that we called z. And when we made that substitution, this integral became these two integrals. And making the substitution z equals the secant of theta, this turned into a trig integral that we evaluated, and we got this expression. And here we have secant theta, cosecant theta, cotangent of theta, and we have to get this expressed now in terms of z. And of course, you know what this is. The secant of theta is just z, but we have to determine the cosecant of theta and the cotangent of theta. So we do what we did before. We draw the triangle. Here's the angle theta, and the secant of theta, which is z, that's equal to the hypotenuse divided by the side adjacent. Secant of theta is z divided by 1. So this side here is to be the square root of z squared minus 1. So by looking at the triangle, we can immediately determine what the cosecant is and what the cotangent is. So we can make these substitutions and get this expressed in terms of the variable z. Before we do that, let's take a look at this integral, because again it has the same denominator here. So we're going to evaluate it in the same way. We're going to say let z be equal to the secant of theta. So z squared minus 1 would be the secant squared theta minus 1, or this is tangent squared of theta, and dz, that is the secant squared of theta times the tangent of theta d theta. So this is going to be equal to 2 dz is this secant of theta times the tangent of theta divided by the tangent squared of theta d theta, and these are going to cancel. So we have 2, the integral of the secant of theta divided by the tangent of theta d theta, and it seems like we just did this. This is the cosecant of theta here. So this will be equal to minus 2 times the natural log of the cotangent of theta plus the cosecant of theta. And that's what we have up here, and it's with the same substitution. So to determine the cosecant of theta and the cotangent of theta, we're working with the same triangle here. So this integral here is minus 2, so it'd be 2 secant theta minus 2 times this minus 2 times this, or just minus 4 times this, and that would be with these two integrals combined now. So the cosecant of theta, that is the hypotenuse divided by the side opposite the angle, and the cotangent of theta, that is the side adjacent divided by the side opposite. So let's get all this now expressed in terms of the variable z. The secant of theta is just z, so we have 2 times z minus 4 times the natural log of the cosecant of theta plus the cotangent of theta, and this right here is a square root sign. Hypotenuse is z divided by the side opposite. So this is going to be the cosecant plus the cotangent, z plus 1 divided by this common denominator. And this common denominator, the square root of z squared minus 1, this is the difference of two squares. So let's write it like this. Square root of z plus 1 times the square root of z minus 1. And z plus 1 divided by the square root of z plus 1, that's just going to give us a square root sign in the numerator. Or we can rewrite it like this. That will be 2z minus 4 times the natural log of z plus 1 divided by z minus 1 to the 1/2 power. And using our property of logarithms, we can modify this further. That will equal 2 times z minus 2 times the natural log of z plus 1 divided by z minus 1. And now we can go back and do our substitution for z. Z equals the square root of t plus 1. And furthermore, once we put this, replace the z with this expression, we have to put the limits in, which means we evaluate at t equal to 8 minus t equal to 3. So let's change this to a plus sign. This would be equal to 2 times z plus 2 times the natural log of the reverse of this, z minus 1 divided by z plus 1. Okay, now we can substitute for z. Here we're going to have 2 times the square root of t plus 1. T goes from 3 to 8 plus 2 times the natural log, the square root of t plus 1 minus 1 divided by the square root of t plus 1 plus 1, and t goes from 3 to 8. So carry out this evaluation. If we don't make any mistakes, that should finally be the solution to this integral here. Okay, 8 plus 1 is 9. The square root of 9 is 3 times 2 is 6. Minus, when 3 is 1, when t is equal to 3, that's 3 plus 1 is 4. The square root of 4 is 2 times 2 is 4. Plus 2 times the natural log. Square root of 9 is 3. Minus 1 is 2. Divided by 3 plus 1 is 4. And we'll have minus 2, the natural log. T is equal to 3 now. 3 plus 1 is 4. Square root of 4 is 2. Minus 1 is 1. And this is 2 plus 1 is 3. Before we go further, let's check ourselves. 8, this is 9. The square root of 9 is 3 minus 1 is 2. 3 plus 1 is 4. Minus now when t is evaluated at 3. This will be the square root of 4, which is 2 minus 1 is 1. 2 plus 1 is 3. So this will equal 6 minus 4 is 2, and we can write this as a division here, plus 2 times the natural log of 1/2 divided by 1/3, or that would be times 3. So this equals 2 plus 2 times the natural log of 3/2. So this here then is this integral here, evaluated at the limits, t going from 3 to 8. Okay, and again, it wasn't that difficult to solve. There's a lot of steps involved, but the whole thing hinged upon making this substitution step right here. So that's it for this video. We have 2 more videos prepared involving integrations that incorporate a radical expression. So come back and join us for those, and we'll see if we can solve some more problems.